All right, so we're going to talk about line integrals today. So we're in section 15.2. So line integrals are similar to single integrals, except we're evaluating them along a curve rather than along an interval. So a single integral in single variable calculus, we're evaluating an integral along the x-axis. So that's our boundary. Now our not our boundary, but that's the curve that we're integrating over is the x-axis. We're going from x equals something to x equals something else, and we're integrating. So we're finding the area below the curve above the x-axis. So we're doing something similar with line integrals, except instead of the x-axis, we're going to evaluate a function above a curve. So really, a curve integral or path integral would be kind of a more accurate description. And an example of how we would use a line integral would be if we had some curved piece of wire, and the density function was a function of x and y, and we would integrate the density over the little piece of length, and we'd get the mass of the wire. So what we do for line integrals is we want to find the sum of some function x in the plane, sum of f of x, y over a path or curve. And we call our curve C. So our basic procedure is we write our curve, we express our curve as parametric equations. And we're going to say x is some function of our parameter t, and y is some function of the parameter. For on some interval, a is less than or equal to t less than or equal to b. And we're assuming that C is smooth. And a smooth curve again means that the first derivatives are continuous and they're not zero at the same time. So we're going to draw a picture and represent what our line integral, what our curve integral is telling us, and then we'll figure out how to evaluate it. So we're going to follow the same procedure we did for finding surface area, for finding volume using multiple integrals. And by now the argument that we use should be pretty familiar. So here are our axes. And we have some curve in the plane. And we're starting at p sub 0, and we're going all the way out to p sub n. And we're saying that p sub 0 corresponds to t equals a, and p sub n corresponds to t equals b. So this is our curve. We've written our curve as a parametric equation, and we're going to divide it into little intervals. So this is P0, this is P1, P2, and up here we're going to talk about some arbitrary interval. And the length of that interval is delta S sub I. And inside that interval is our point x sub I, y sub I. So each small arc is length delta S sub I. And we want to form the sum. We're adding up the sum of our function value at this little position times the arc length. So we're summing from I equals 1 to n of our function times delta S sub I. So again, if this were a wire with a density function f of xy, this sum would give us the mass of the wire. The density function is a function of position. So the mass, the density times the little piece of length would be the mass, and we're going to sum it over the length of the wire. And x sub I, y sub I is a point in this little ith subarc. And we're going to take the limit as delta S sub I gets smaller and smaller and smaller, just like we've done before, and we come up with our definition of our line integral. So our definition of a line integral, and notice here that we're taking the line integral today, we're working on the line integral of a scalar function. F of xy is a scalar function, so we're summing this scalar function over this curve. Tomorrow we'll talk about how we sum a vector function over a curve. So our definition of a line integral of f along C, and we write that as the integral of C of f of xy ds is the sum, the limit, as delta S sub I approaches 0 of the sum I equals 1 to n of our function times our arc length. So that's our definition of a line integral, is this limit of this sum. Just like we define, it's very similar to the way we defined a multiple integral. We define a multiple integral as a sum. So our line integral is just this sum. Good morning.
Yeah, I was thinking of alarms and both of them didn't.
That's cool, man. Now it's a square.
Yeah, there we go.
Nobody can hear anyway. So here's our definition of a line integral. And just like we did with multiple integration, this doesn't really tell us how to evaluate this. We need a way to evaluate this. So we need to do a little more work with this to come up with an easy way to evaluate this. So let's work on that. So evaluating line integrals. So remember from chapter 13, way back when, we said that our arc length parameter, our arc length increment, was the magnitude of r prime of t dt. where r is a position function. So if we have a parametric equation for our function, the arc length increment was the magnitude of r prime times dt. And we figured out that this was the square root of dx dt squared plus dy dt squared. dt. This was our arc length parameter. We can show that if f is continuous, that the integral, that our line integral, the integral over our path of f of xy ds is the integral from a to b of our function represented in terms of our parameters times our arc length parameter. And we're saying that x is some function of t. X is represented by a parametric equation. Y is represented by a parametric equation. And a is less than or equal to t, less than or equal to b. And we can also write this, we can write this in a little shorter notation. We can say that the line integral of f of xy ds is the integral from a to b of f of xy times r prime, magnitude of r prime dt. So this gives us a way to evaluate our line integrals. A couple of important things about line integrals. When we parameterize our path, when we parameterize the curve, we're introducing an orientation. So we're saying this direction is positive. So if we look back at the drawing that we made, here we're saying we're going from t equals a to t equals b. So we're going this direction along our path. When we introduce that parameterization, we're saying this is the positive direction. So our parameterization introduces an orientation to the curve. Also note that if our function f of xy is 1, so if it doesn't vary with x and y, our line integral just gives us the arc length of our curve between a and b. If f of xy is 1, so if it doesn't vary, if f of xy is just 1, then the integral over our curve of ds is just the arc length of the curve. And this is how we define the arc length of a parametric curve. And we can also think of the line, if our function, if f of xy is positive, we can think of this as an area. So if we think of our path as some curve in the plane, and f of xy is positive, so we have f up above our curve. F of xy is going to be this distance. So we can think of the line integral as, and we're going to call this one as our curve C, and this is from A to B. We could think of the line integral as the area of this fence. So f of xy is some function that's up above our curve. Then the line integral is the area of the fence that goes along the curve that's above the curve somewhere. So we could think of the line integral as an area if f is positive. So that's another way to visualize it. And if we want, we can go through the same arguments for a line integral in space. If we have f of x, y, z, and our curve is in space, we just add our z component and everything. The same arguments hold. Everything stays the same. And we can also make the same argument if our curve is piecewise smooth. And by piecewise smooth, so we said that our curve, in order to take a line integral, our curve had to be smooth. We can divide, if our curve is not smooth, if we can divide it into pieces that each one is smooth and we can connect them together, we can still do our line integral. So a piecewise smooth curve would be something like, draw an example of a piecewise smooth curve. So if we had something like this, something like that, so a piecewise smooth curve is, and we'll just divide this into C1, C2, C3, and C4. So we just divide it into pieces that each piece is smooth over a certain interval, and then we would sum our line integrals over these four curves. So we can form a line integral over piecewise smooth curves just by breaking it into pieces. And any other physical interpretation of a line integral really depends on the interpretation of our function and of our curve. All right. Questions before we do a couple of examples? All right. So we've defined our line integral. We have come up with a way of evaluating it. We've given it a couple of interpretations depending on how we want to interpret the curve and the function. And we've talked about piecewise smooth curves where we can just sum our line integrals over the curves. Now I want to go back briefly and just remind us about finding parameterizations. We practiced with finding parameterizations earlier in the semester. So we want to parameterize the curve x squared over 16 plus y squared over 9 equals 1. So we want to parameterize this curve. So first of all, what is this? What is this curve? Circle? Ellipse. All right. And our major axis is vertical or horizontal? Horizontal. So if I drew an ellipse here, something like this, and we'll parameterize it going counterclockwise. So what would be a good parameterization for this ellipse? X equals, remember how to do this? We have x squared and y squared and this equaling 1. So we think sines and cosines? Oh yes, that should be y. So x equals, let's let x equal 4 cosine t and y equal 3 sine t. For 0 less than or equal to t less than or equal to 2 pi. So if I square x divided by 16, square y divided by 9, I just get sine squared plus cosine squared equals 1. So that would be a parameterization for this curve. So we could say that r, our position function, because when we're doing our line integral, we need r prime. So our position function along that curve is 4 cosine t I plus 3 sine tj. So our first step in doing line integrals is to parameterize our curve, and then we have to find the magnitude of r prime. That's what we came up with for how we evaluate line integrals. Let's parameterize a piecewise curve. So here is our curve. Draw a picture. So we want to parameterize this curve, and this is y equals x squared. This is the point 2, 4. This is y equals 4. So this is 0, 4. And this is 0, 0. So we want to parameterize this piecewise smooth curve. So I'm going to break it up into 3 pieces. Let's call this C1, C2, and C3. So for C1, what would be a good parameterization for the first curve here? X equals let's make it easier. Instead of roots, let's go the other way. But x equals t, y equals t squared, and we're going to let 0 less than or equal to t less than or equal to 2. So that'll take us along that curve. For the second curve, how are we going to parameterize that? For this one? What is y? So y equals 4. And we want to move from 2, 4 to 0, 4. 2 minus t. So x equals 2 minus t. And t varies from 0 less than or equal to t less than or equal to 2. And for our third curve, finally, what do we have, Danny? X equals 0, and y equals 4 minus t. For 0 less than or equal to t less than or equal to 4. So our path r of t would be the union of these 3 parameterizations. So we'd have a piecewise, this would be a piecewise smooth curve, and our parameterization would be the union of these 3 on our intervals. Let's start ringing some bells, what we did kind of back near the beginning of the semester. All right, let's evaluate a couple of line integrals, and then we will be done. We want to evaluate the integral along C of 4xy ds, where C is R of t is ti plus 2 minus t j for 0 less than or equal to t less than or equal to 2. So this problem is nice. They give you the parameterization of the curve already. So if we don't have the parameterization of the curve, we have to come up with a parameterization to evaluate our line integral. So to evaluate our line integral, we need r prime. So r prime is I minus j. The length of r prime, we need the length of r prime, is just the square root of 2. So our integral of 4xy ds, it's not cooperating, ds, is the integral from 0 to 2. Our function in terms of our parameterization, so x is we have 4 times x is t, and y is 2 minus t. And then we have r prime dt, so square root of 2 dt. So this is just this is 4xy represented in terms of my parameterization. So this is 4 square root 2, the integral from 0 to 2 of 2t minus t squared dt. And when I evaluate that out, I get 16 square root 2 over 3. So to evaluate my line integral, I need a parameterization for my curve. I need to represent the function in terms of the parameterization and substitute. I need r prime. My ds turns into the length of r prime dt. And then I plug all of that into my integral and evaluate. Questions on that? Line integrals of scalar functions are pretty straightforward. We just need to remember there's, right. Let's look at another one where we have to parameterize our curve. So we want to evaluate the integral of x squared plus y squared along our curve C ds and along our curve is counterclockwise around x squared plus y squared equals 4 from 2, 0 to 0, 2. So we have our curve. We need to parameterize our curve. So what would be a good parameterization for this curve? What is this curve? Circle. And we're going counterclockwise from 2, 0 to 0, 2. So we're going from here to here. That way. So we need to parameterize this curve. What would be a good parameterization of a circle? X equals 2 cosine t. Y equals 2 sine t. And if we're going counterclockwise from here to here, we're going to say that 0 less than or equal to t less than or equal to pi over 2. So our parameterization for the curve, r of t, is 2 cosine ti plus 2 sine tj. R prime of t is minus 2 sine ti plus 2 cosine t j. The magnitude of r prime is just 2. And now we represent our function in terms of our parameterization. So x squared plus y squared in terms of our parameterization of our path is what? On our path, x squared plus y squared equals 4. So our integral, so the integral along c of x squared plus y squared ds is just the integral from 0 to pi over 2 of 4 times the magnitude of r prime, 2 dt, and that is just 4 pi. Parameterize our curve, represent our function in terms of the parameterization, and ds becomes our prime dt. Plug that in and evaluate. Let's see, we get 8 dt, so we get 8t from 0 to pi over 2. We good? All right, are we good on line integrals with scalar functions? If we have a piecewise smooth curve, we just sum the line integrals over each piece of our curve. Same procedure. Parameterize your curve, represent your function in terms of your parameterization, and then ds becomes the length of r prime times dt, and add those up. Okay. Homework. Page. Did you already do it, Scott?
Yeah, I just caught up.
All right, there you go.